Okay, we left off in part 1 talking about how we could use polygons to approximate the area of a circle. Okay, it turns out we can generalize that to approximate the area of any curve, and the polygon that we are going to prefer to use is the rectangle. Okay, so here we have a function negative x squared plus 5, and we want to find the area underneath this function, okay, bounded by the x-axis here, and x equals 0 and x equals 2. Okay, so this whole area underneath the curve. We are going to do this using several rectangles. Okay, in this case, we have 5 rectangles, and you'll notice that since there are 5, and let me try a different color. Since there are 5, and we're going from 0 to 2 on the x-axis, each one has an equal width of 2/5. All right, each one has an equal width of 2/5. All right, and the height of each one is determined by a value, a point on the function. Okay, so if we want to know what the height of this is, we would just take the x value here, 2/5, and plug it into the function. So f of 2/5 will give us the height there, f of 4/5 will give us the height here, 6/5, 8/5, and 2, and so on. Okay, so we are going to use these 5 rectangles, and we're going to actually do this approximation 2 ways. One with rectangles that are all below the function, and then our second type is with rectangles that are all above the function. But you notice they all still have the same width. The only difference is instead of the right side of the rectangle determining the height, the left side determines the height. So now if we want to find the height of this rectangle, we would plug in f of 0, okay, f of 2/5, f of 4/5, f of 6/5, and f of 8/5, so slightly different. Okay, so the first thing we need to do is look at our rectangles, and as we do this, we want to conceptualize, because yes, it's true, we could take 2/5 times the height plus 2/5 here times the height plus 2/5 times the height plus 2/5 times the height plus 2/5 times the height, and add all of those up one by one, but that is hard work, okay? We want to try and abstract that into a sum, okay, and that's where the summation rules that we saw before come in handy. All right, so rather than area plus area plus area plus area and one more plus area, we want to write it as the sum as I equals 1 to 5 of AI. So the area of the ith rectangle from 1 to 5. All right, so the first thing we need to do is talk about what this area means, and I've already told you it's height times width. Okay, height times width. And again, we already specified what is the height of the ith rectangle. Well, it is the function evaluated at a point in the ith rectangle. We're going to call that point CI. And the width is something we're going to call delta x, which for this case is all of them are equal. We see that it's 2/5 by looking at the picture, but we could also note that it's 2/5 by using this formula. Delta x equals b minus a over n, where b is our left endpoint, so 2. A is our right endpoint, so 0, divided by the number of rectangles, which is 5. So that would be 2/5. All right, so height times width is our area. All right, so now for the first set of rectangles, we are determining this sum and setting it up using the right endpoints. So we need to conceptualize what's a way to represent these right endpoints. Okay, for this particular one, the right endpoints are 2/5, 4/5, 6/5, 8/5, and 10/5. All right, so those are the values. Now we need to figure out what thing do we need, what do we need to put that in terms of I, okay? So if I is 1, what makes us get 2/5? If I is 2, so our I values correspond to, when I is 1, we want to get 2/5, 2, we want to get 4/5, 3, we want to get 6/5, 4, 8/5, and 5, 10/5. All right, so by simple division, you can see that if we choose our expression to be 2/5 I, we will get this. So if I is 1, we get 2/5, 2, 4/5, and so on. All right, so setting up our sum, we're looking at the sum from I equals 1 to 5 of the height, which again is the function at this particular point, which in this case, we're going to call this 2/5 I, times the width, which is 2/5. All right, so now we take 2/5 I and plug it into the function that we're given up here. So this is 5, I equals 1 to 5, sum of negative 2/5 I squared plus 5, all times 2/5. All right, from here, it's actually a pretty easy summation problem, okay? So we rearrange and get it to where our I is by itself. It's squared. Do the sum. All the others are constant. I'm not going to go through all the details of that for this particular example. But we end up with a single number value, and that is 162 over 25, which in decimal form is 6.48, which we will come back to. Okay, these are the rectangles that are under the curve, also called the lower sum. Okay, all right, the second example here requires us to use the left endpoints. The left endpoints are slightly more difficult to grasp. Okay, in this case, the endpoints are 0, 2/5, 4/5, 6/5, and 8/5. It ends at 8/5. Yet, we want when I is 1 for our x value to be 0, when I is 2, 2/5, 3, 4/5, 4, 6/5, and 5, 8/5. Slightly different than we saw before, okay? So, you may notice that this is a shift of 1 of delta x by 1. So the magic trick we use is that the left endpoints, and this is actually true for any left endpoints that start with x equals 0, that our expression will be delta x times I minus 1. And that fulfills when I is 1, this cancels out, becomes 0. When I is 2, it's 2/5, and so on. Okay. So now that we have in the expression, that's probably the hardest part. For our particular problem, it's going to be 2/5 I minus 1. Another way to write that, 2I minus 2 over 5. Okay. So now we plug into our sum. The sum as I equals 1 to n of f of 2/5 I minus 1 times our width, 2/5. Okay. So, plugging in to our original function, x squared, negative x squared plus 5, we get sum I equals 1. I'm sorry, this should be a 5, not an n. Okay, sum of I equals 1 to 5 of negative 2 over 5 I minus 1 all squared plus 5 all times 2/5. Okay, Again, I'm not going to go through all the algebra to simplify this and find the sum, but our final answer is 202 over 25, or 8.08. Okay, and that's our that's our upper rectangles, or the ones that are above the curve. All right, now it's important to go back and look and compare the two. Okay, so the lower rectangles obviously were, the value was smaller. The upper rectangles, it was bigger. What is the actual area? Okay, because we know that all of the rectangles that were under were the lower rectangles, that is definitely got to be smaller than the actual area under the curve. Oops. And we know that the upper rectangles, the sum of the upper rectangles, got to be greater than the area under the curve. Okay, so our actual area is somewhere in between the two. Okay, what is it that we need to do to get a closer and closer approximation? Okay, this goes back to what I said in the last one, that if we can make the difference between the under and the upper, or the lower and the upper, if we can make the difference between the two smaller, we can get a better and better approximation. And one way we can make the difference between the two smaller is to increase the number of rectangles. Okay, well, you saw how tedious it was to just do 5, so we are going to learn some techniques that make things a little bit simpler. But I will go ahead and tell you, if you increase to 25 rectangles, you find that the lower sum is 7.17 and the upper sum is 7.49, which is a much better range to deal with. Okay, given the problem that we did here, we just know it's probably around 7, maybe 7.25, somewhere in there. This narrows it down quite a bit more. Okay, so as we increase the number of rectangles, we increase our area. We increase our closeness to the actual area.